And the base rotates too, it says?
Everything rotates.
That's pretty awesome.
How do you classify this?
Hey, how are you?
Brilliant. That's how you classify.
Full there.
Might have to go around. I recommend you go around, unless you think you could fit.
That's a good tip.
Who made that?
GK?
GK?
That's pretty neat.
Wonky.
No. GK somebody else.
That's one way to get XY pattern, right? It's like the two swivel head idea, like bug eye lamps and other things, but with a different take, you know? It's like on one axis.
And a jack.
Oh, for a sensor, I think.
How much is it?
I haven't got a price yet. Yeah.
The base rotates too.
So you guys feel ready to get started?
Yep.
Okay. You know, Greg had asked me to try to start giving some training and some sort of, you know, understanding to some things that will lead into a better way to work with LED drivers, LED power supplies, and things like that. And one of the things I thought of doing was to jump right into a data sheet for an LED driver or something like that and start telling you what all that stuff means. I think that's really important, and I think we will do that at some point, probably the next session. But I had another idea. I had an idea about something that through the 30 years of my career I've seen people kind of trip over time and time again. They're ideas about energy and about efficiency, okay, and about power. And there's some mysteries involved in there, but the interesting thing is it all revolves around some very simple principles. And they're valuable because a lot of managers, even if you start off as an electrical engineer or an electronics expert, sometimes you get into management and then you start not using that knowledge and you start losing that knowledge. Also, many managers don't even have that background. You might be a mechanical engineer, right? Or you might have no engineering experience whatsoever. And you may not even have a clue as to where to start to answer some questions about, hey, how efficient is this driver? Or where's the heat coming from? Or how can I get my LEDs to work a little more efficiently? What's a switch mode power supply? What's a linear power supply? All these things become confusing because you don't have the experience. But the good news is that you can learn a lot about your problem and what to do as a manager without deep diving into electronics if you know some fundamental principles about energy. Now, some of the things that I talk about today are going to seem very, very basic. They're going to remind you of high school maybe, if you took some of this in high school. And certainly if you had engineering courses, you might feel like, you might do some eye rolling like, yeah, I know this. But we're going to take it through a step where we look at energy and we look at power and efficiency in a way that applies to what we're doing here. Okay, and you're going to see that it's a very powerful technique. So the three things that I want to talk about today is what we call conservation of energy. It is a very important concept. All right, we're not just going to tell you what it is because you can do that in about 2 seconds, right? But we're going to show you how you can, how this works with what we're doing in power supplies, electronics, and lighting. We're also going to talk about power, okay? What is power, right? And how that relates to conservation of energy. And we're going to talk about efficiency. Okay? And we're going to talk about these three things and how they relate to electronics, and more specifically of lighting or power supplies. Okay? So let's start with the first topic that I want to talk about, which is conservation of energy. And bear with me if I start to sound like it's a little bit of storytelling, but I think it's really important to help kind of burn in some very basic ideas. So we're all in the universe, okay? And in the universe, which is everything, it includes the table, this chair, all of you, so on, there's energy. There's little pieces of energy everywhere you go, okay? There might be a jelly bean on the table. If you eat it, you get some energy from that, right? Maybe down the hall, there's a cup of coffee. You can drink that, you get energy. There's gas in your car outside, there's energy. Out in interstellar space, there's a sun that's producing energy. There's energy everywhere you go. I'm going to write these little E's to kind of tell you about, well, to kind of indicate little packets of energy that are everywhere, okay? The concept here is that we can take a subset of the universe, let's say this room, for example, and we can draw a line around it. And when we've done that, and it could be anything. I could take this chair, for example, to be the subset of the universe that I want to draw an imaginary line around. Okay? I haven't done anything. I created a line that really doesn't exist. But what I'm saying here is that I've cut the universe into two things. A part that's on the inside, which I call the system, and the part that's on the outside, that I call the environment. And the two of these form the universe. Now the beautiful thing about this is I can make this line around anything I'm interested in. So let's say I did this chair, for example. Some of the energy is in the system. I could take this chair and I could throw it in a fireplace and burn it, and it'll give me a lot of energy, right? So there's energy in this chair right now. And there's energy outside, which I call the environment. Like me, for example. I could have a flashlight that has batteries in it that has energy. When I go and aim it at the chair and I turn on the flashlight, I can put energy from me to the chair. So we can move energy, okay, from the environment into the system. But, and this is the point about conservation of energy. Conservation of energy says I cannot just add an E. I can't do that. There's all these E's in the universe, but I can't create one. I also can't delete one. Can't get rid of it. I'm not allowed to do that. Put that back. Okay? They're conserved. They're like M&Ms. There's 100 in a bag. They don't disappear unless you eat them. But we're not allowed to do that. Okay? Which means that if I put energy into the system, if I say, oh, I'm going to take this one that's in my flashlight and I'm going to put it into the chair, okay? It can go in here, but it's got to come out from here. You can only move it. You can move it around. You can move these E's around, okay? Same thing here. If I say, well, the chair is, let's say, warm, and it's giving off its warmth back to the environment, an E can leave the chair, but only if it goes into the environment, okay? So we have energy that can be moved around. It can go in, and it can come out, but it can't just be erased. It can't disappear. This is really important, as we'll see how this plays out. Now, I'm going to jump a little bit ahead, and I'm going to talk about, well, no, I'm not. I'm not going to talk about power yet. Let's stick with energy for a while, because we have a lot of things to talk about here. So what this kind of means is that the amount of energy that's in my system, okay, can change. If I take energy from the environment, let's say I take two pieces of energy from the environment and I put that into my system, okay, these two. I had two going in. That means because they came out of here, this increased by 2 on the inside, okay? So it's important to understand that as I'm adding energy into the system, the amount of energy in the system starts filling up. Likewise, if I were to pop a leak in here and allow these E's to come out, okay, I would find that the amount that leaves reduces how much is inside the box. Now this gets a little confusing when we talk about packets of energy because they're sort of ethereal. We don't really know what they are tangibly. So I'm going to use an example here with water. Okay? Instead of energy, okay, let's talk about gallons. I have a lot of gallons out here. Okay? The universe has a lot of gallons. I have some gallons inside my system. Okay? And maybe my system is a container, okay, that can hold these gallons. Now what I'm going to do is I'm going to take a faucet and I'm going to put gallons into my system, okay? Now it's starting to maybe feel a little bit more comfortable to everybody. And I'm also going to put a hole in the bottom of my tank, and I'm going to let gallons flow out, okay? Let's say I have a flow rate here, okay? A flow rate of, I don't know, 20 gallons per minute, okay? And let's say I have a flow rate coming out of the bottom of, let's say, 5 gallons per minute, right? Can anyone tell me, this should be pretty basic, what's happening to the tank in here if I have 20 gallons coming in and only 5 gallons coming out? It's filling up, right? More is coming in that's going out. If you have a warehouse that gets 20 boxes a day and ships out 5 boxes a day, you got 15 more boxes you don't know what to do with, right? And the next day you'll have 30, and the next day you'll have 45, so your warehouse is filling up. Seems pretty basic, right? But this is all because of conservation of energy. This is because none of these boxes can just magically disappear, okay? So this tank is going to fill up at what rate? What rate is this tank going to fill up? I just said it a second.
15 gallons.
15 gallons. Does everyone know why that is? It's because 20 is coming in, and 5 is going out, so there's 15 that's got to go someplace, right? So this thing fills up at a rate at 15 gallons per minute. Well, we're okay, we're comfortable with this, right? So what if instead of these things being gallons, I made them M&Ms, right? It'd still work, right? 20 M&Ms go into the box, 5 M&Ms come out of the box, there's 15 M&Ms left over every minute, so the box fills up with M&Ms. So what I'm going to do is I'm going to change these things called gallons into something that are packets of energy called joules, okay? Remember those E's I drew on the board, those little E's, the little packets of energy? We have a name for those things, and they're called joules, okay? It's a unit of energy, okay? So instead of having gallons in my universe, I have joules, okay? Instead of having 20 gallons per minute flowing in here, I have 20 joules per minute flowing in here. Instead of 5 gallons per minute coming out, I have 5 joules per minute coming out of here, okay? And instead of having a tank inside here which can hold a certain number of gallons, okay, I'm going to have something that holds a certain number of joules, okay? Keep that in the back of your mind. What happens when this system, let's say the system can only store so many gallons, what happens when it fills up? Remember I said there was 20 gallons per minute coming in, 5 gallons per minute coming out, 15 gallons per minute is how fast this tank is filling up. What happens if this tank holds 15 gallons? What happens in 1 minute? Fills up. Pretty basic, right? 15 gallons per minute is the surplus. Let's go back to the warehouse. Got a warehouse. 20 boxes come in, right? 5 boxes go out every minute, okay? So after a minute, you've got 15 boxes. What if your shelf can only hold 15 boxes? What happens in a minute? You're full. What happens in the next minute? Okay, what happens when the 15 gallons is full, 20 gallons is still coming in, 5 gallons is still coming out? What happens? What happens?
Flow rate changes.
What happens?
Flow rate goes to...
I'm telling you the flow rates aren't changing. I'm telling you I'm pushing 20 gallons in here.
Oh, okay.
And I'm telling you only 5 gallons is being taken out. What happens?
Pressure increases.
Yeah, but at some point what's going to happen?
Overflow.
That's right.
Oh, okay.
That's what will happen. It will overflow. Okay? At some point, you will now have 15 gallons per minute overflowing. Okay? It's like this chair. I put a heat lamp in front of this chair. Okay? This chair is at some room temperature, and I put a heat lamp. I'm starting to put energy in. Okay? And for a while, the chair just warms up. It soaks up that energy. Now, that's not perfectly correct. There's a lot of things happening, but just run with me on this. The heat heats up the chair until it reaches some point where it can't take any more heat. Okay, and that has to do with when it's losing the same amount of heat that it's gaining, but in the simple example, it reaches a certain point where it's at equilibrium. It will not accept more energy even though you're putting it in there. what is it doing at that point if it's not raising temperature anymore? Its tank is full. It will not take any more energy. So the energy you're putting in is exactly what's coming out, okay? That's an important concept. So let's go back to these things called joules, okay? I have some overflow. I have some inflow. I have some outflow, okay? And I'm telling you, instead of gallons, I'm going to call them joules, right? So this tank holds 15 joules. It's rising at 15 joules per minute. It has 5 joules per minute coming out. Now I'm going to change minutes to seconds, because I can do that. Yeah.
So in that case, when it's overflowing, it's only going to be overflowing 10 joules a minute because you're still releasing 5 joules a minute from the bottom, correct?
No, that's not right, because you have 20 joules coming in, okay? You have 5 joules coming out. So this was rising at 15 gallons per minute. And just like if you had a pool that you had it rising at 15 gallons per minute, it hits the top. When it hits the top, you have 15 gallons per minute coming off, right? You have 20 coming in, you have 5 coming out, you have 15 left over, right? I'm going to change minutes to seconds, only because I only measure this in terms of seconds instead of minutes. I can do that. It's still a unit of time, right? So 20 joules per second, it's a little bit faster now. I got 20 joules per second. I don't have to wait a whole minute for it to happen. I have 5 joules per second, right? I have 15 joules per second. Well, guess what joules per second is? Does anyone know? This is what I'm saying. If you don't know that, all your engineering training failed you, okay? This is really important stuff, because if you know these few things, you can answer a lot of questions, okay? Joules per second is a unit of power called a watt, okay? So now you see drivers, it's 100 watts, power supply 55 watts. You know what they are. It's a flow. It's gallons per minute. All right? It's how many of these energy units out in the universe are flowing through it, okay, and coming out of it. Watts. So guess what? Over here, instead of joules per second, I have 20 watts. Over here, instead of 5 joules per second, I told you joules per second is a watt, okay? I have 5 watts, okay? Instead of something leaking out of here at 15 joules per second, right? It's 15 watts, okay? This is a unit of power, which is leading into our second topic today, which is about power, okay? Power is simply the rate at which energy is flowing through a boundary, okay? I had the universe, I created a boundary, and I said, look, I have energy outside, I have energy inside, okay? Some energy is flowing in, some energy is flowing out, like toll gates at a bridge, right? Some are coming in, some are coming out. How many pass that gate per second is power, okay? That's power. So what do we have here? I told you that conservation of energy meant that whatever goes in either has to stay inside or has to go out, but nothing's created or destroyed. So what does that mean? It means if I redraw the system where I have my power in, okay, and I have my power out, okay, and I have my power leaving, right, or overflowing. Let's call it overflowing because that was our example. Overflow, right? What do we know? Well, we know that the power in minus the power out equals the power overflowing, right? Okay, so why are we talking about this? You're going to see something that comes in kind of handy here. Let's put this aside for a minute, this thing about the valve and the water and the tank for a second. Let's talk about some electronics that I know about. See if you understand what I'm doing when I do this. So let's say I have some power, electrical power, 120 volts, okay? And let's say that that's going to a bridge rectifier. And let's say that's going to a filter capacitor. Now let's say that's going to a transistor, which is going through a a Zener reference, which is then coming back to a feedback transistor, which is controlling its gate. Okay, and that's feeding a LED. Okay, but the LED has a resistor in series to detect its current, and I take that and bring it back to some feedback with another transistor that I want to use to help control the gate of this to help regulate the current as well. And they ask you, okay, on my LED, I have 40 volts, and I have 1 amp going through it, and over here I have 120 volts with 1 amp going through it. And as a manager, someone asks you, what's the efficiency of the circuit? What's the efficiency? Oh, let me call Mark. He's our electronics expert. He knows all about transistors and diodes and capacitors. I don't know any of that stuff. I never learned any of that. Well, I can use the magic of my system and draw a dotted line around here. Guess what happens to all the inner workings of the system? Who cares? It's gone. It's gone. All the minutiae, all the detail about diodes, capacitors, inductors, transistors are gone. They're gone because I decided to draw the line around the chair. Now I don't care about how many atoms are in the chair. I don't care that it has an arm or legs or wheels. I just drew a whole big box around it. Now it just becomes a system. And because of conservation of energy and power, the same rules apply. So all that tribal knowledge of what's going on, which is extremely important if you have to design something to do something, okay, kind of fall out of the equation because you're not asking that question. You're not asking how does it work, what is the inner workings, what's the power here versus the power there. That's not what you're asking. You're asking what's the efficiency of the circuit, the driver, okay? And I'm going to tell you one other thing about power and as it applies to electronics, and I'm not going to prove this here. It's a little involved, but I'm just going to give it to you. You have to take it for face value. Power equals voltage times current. That's something that's good to know, okay? Power equals voltage times current. There are some pitfalls with this that we're going to talk about later, but for the time being, we'll just multiply them together. Okay, when it comes to I'm going to pre-warn you that when it comes to AC circuits, there's some details about being in phase and out of phase. I don't want to get distracted by that right now. We're going to talk about that later when we talk a little bit more about power and efficiency and power factor, but for now, it's just voltage times current. So let's take a look. What is the power going on right here? Well, what's the voltage? Somebody tell me, please.
120.
120. What's the current?
1.
What's the wattage?
110.
120. I have 120 watts going in. Somebody please do that for me here. 40, right. So I have 40 watts coming out. Okay, so what's wrong with this picture?
It's not balanced.
It's not balanced. I like that. It's not balanced. What's the discrepancy?
80 watts.
80 watts. Where's it going? Into a black hole? Did it vanish? Did it erase?
Heat.
Please don't say yes because I told you energy is conserved. You can't just erase it.
Turns into heat.
Turns into heat, but yeah, that's right. It could be turning into heat. Maybe not. Could be light, right? Could be sound, right? But where is it? Can only be doing one of two things. One's the obvious one, one's the not so obvious one, but can only be doing one of two things.
Going to the environment.
That's one thing it could be doing. That's the most likely thing it's doing. What else could it be doing? Remember we had a tank of water? Could be filling the tank. The tank might not be full yet. Let's give an example. I hook up some kind of a heating pad to this thing. I turn it on, right? For a few minutes, maybe an hour, power is going into the chair, right? But that same amount of power is not coming out of the chair because it's warming the chair, right? It's going into energizing. So if I have a driver, for the first hour or two, and I've turned on power, it's not going to be giving off a lot of energy. That loss is going to be going into heating up that block of goop that's in there or the capacitors or whatever, okay? But the point is, again, at equilibrium, when all things have stopped changing, when everything has kind of been left to do what it does for a while, yes, as Eric said, it's going to come out, okay? So 80 watts is going to come out of here. Okay? Look how powerful these ideas are. Okay? I was able to answer the question, what's the efficiency of this driver, without knowing anything about the driver. In fact, you could do the same thing for motorboats and Formula One cars and stars. Okay? You can draw lines around them and you can say power in equals power out, you know, or power in minus power out equals some leftover that's building up in here or spilling over. Okay? So now we're going to go into another idea, which is efficiency. Okay, we're going to talk about efficiency. Let me see how we're doing on time, because I really don't want to go too far over. Give me a second. Okay. So what is efficiency? Does anyone have anything to say about efficiency so we can make this a little interactive? All right, let's go back to M&Ms. All right.
Output over input.
Right. We're going to get to how that's derived. Let's go back to M&Ms. Let's say I got a friend that loves M&Ms, and I like to send him M&Ms. I put 100 M&Ms in a bag, and I have a couple of people I use to carry the M&Ms over to my friend who lives down the road. The first guy that I give a bag of 100 M&Ms to and say, give this to my friend down the road, when it gets to my friend down the road, who knows, maybe he dropped a few, maybe he ate a few, he only got 90 M&Ms, right, out of the 100. I use another guy, I say, I don't like that guy, I use another guy, when it gets over to him, only 17 M&Ms get over there, and I go, okay. Then I type my other friend who's close to me, I say, listen, can you bring this to so-and-so, when he gets there, 100 M&Ms get there. So now I've got these three people. One of them brought 100 out of 100. Another one brought 80, whatever I said, out of 100. Another one brought 17 out of 100. So I want to figure out next time, who do I use, right? This is efficiency. How efficient is this person in carrying M&Ms to my friend? It's a measure of how much gets there. Well, I told you that these energy dots are like M&Ms or like something else that's conserved. It's the same story. If I put 100 joules of energy into my power supply, how many joules of energy get to my friend, the lamp, right? If I put 100 joules in, do 99 get there? Does 87 get there? Does only 17 get there? Well, look at this picture. In 1 second, how many joules did I put into this system I'm using as an example? Can anyone answer that? In 1 second, how many joules are going into this example on the board? 120, because there's 120 watts, which is what? Joules per second. In 1 second, it means 120 goes in. How many is going out to my friend?
40.
40. So another 80 is being eaten along the way, right? Somebody's dropping them or eating them along the way. They're lost, right? This is my power in. This is my power out. This is my power loss, okay? How many do you get to your friend divided by how many you put in is the efficiency. And if you want that in percent, times it by 100. And that equals the percent efficiency. Let's see if that makes sense to us with the M&M model. My friend got 17 M&Ms. I sent 100. 17 over 100 is 0.17%, is 17%, right? In this example, let's do it for this example. Let's find out what the efficiency is of this example right here. So what is my power output?
40.
Right. Eric, you're not allowed to answer for a few minutes because you're the only one answering. I think you get it. So we're going to pause you for a bit to force other people to say something. So I know that people are learning. So 40 are going out, right? How many are going in?
120.
120, right, not 100. Like the M&M example, it's 120. So what is my efficiency? Can somebody calculate that for me?
0.3.
That's right, 0.33. It's 33.33%. Let's just make it 33%, okay? This system is 33% efficient. Is that good?
Depends on.
Yeah, it depends. It depends what you're comparing it against. By today's standards, I would say that's pretty bad, right? You know, but if you're stuck on a desert island with Gilligan and had to put something together with what's left over from the SS Minnow, it might be pretty good. So, depends on your frame of reference, but yeah, it's not so great, okay? Can we do better? Okay, can we do better? How can we do better? I had a tank, and let's draw it here on the tank. I had 120 gallons per minute coming in, and my load was taking 40 gallons per minute out, right? And after it stabilized and my little tank got full, okay, 80 gallons per minute was pouring over the side. So basically had too much coming in, right? Now, assuming I cannot stop how much goes in and I cannot stop how much goes out, can I do better? We can do better.
Bigger tank.
We can do with a bigger tank because it'll delay how long it takes to overflow. But still, at some point, no matter how big of a tank you use, it will reach the top and overflow. And that will just postpone equilibrium, right? You're right. It's like saying, oh, I have a driver, and the driver is, 1 pound. So I'll just make it 100 pounds, and now it'll never give off heat. I wouldn't say never. It'll just take 100 times longer for it to get warm, and then it'll eventually be giving off heat. And in the end, your efficiency is not going to change. Because whether the surplus is going into internal energy or whether it's spilling overboard, it's still not going to your friend who wants the M&Ms. Okay? It's still falling on the ground inside the system, or it's being eaten and taken away. Doesn't really matter. It's not getting to the desired target. So it's not efficient, because the efficiency is only how much gets out divided by how much you put in. Whatever happens to it. Remember I said there was two things that could happen? It could either go overboard or kind of get absorbed internally. It doesn't really matter. So it's still bad. Can we do better? We can. Here's where I'm going to show you something. I'm going to show you something about the gallon example here. But first I want to write down, let me get rid of some of this clutter, okay? Let's say I put a valve on this water supply, okay? I can now turn the valve on or off. When I turn it on, 20 watts goes in. When I turn it off, 0 watts goes in, right? And I'm going to describe a system that should be familiar to all of you because we use one of these every day. Not very glamorous, but it might remind you of something like a toilet tank. I'm going to put a little float valve in my tank, and I'm going to connect that to my valve. What happens in a toilet tank? Does anyone really even bother to look at and see how they work? If you got stuck having to fix one, probably like it or not, you had to learn how they work. The way it works is that it fills up the tank, okay, until it gets to near the top where the float is here, and then it shuts off the valve, right? And it stops. And then when you flush the tank, it goes down to the bottom, and that's where the valve starts to open again and water pours back in. It goes through this cycle, okay? So I'm going to borrow from this idea, and I'm going to say, all right, I'm going to be able to turn my valve on and off in two places. It's going to turn on when it's at the bottom, and it's going to turn off when it's at the top. All right? We're going to see what happens with this system, okay, in terms of energy and power, because we've already discovered that water going in and out of a tank is the same thing in many ways as energy going in and out of a system, right? So we're going to do the same thing. So let's clean this up a little bit so you can really see what's going on. We know it's a system, so we're going to get rid of that word. We're going to get rid of some of these arrows. Okay? This is where it's going to get a little fun. All right, so the system starts off like this. The tank's empty, okay? Maybe there's just a little bit of water left in it. We know that this is going to drain out 40 watts, all right? Which we're calling 40 gallons per second, right? And let's say for argument's sake, okay? Let's say that the tank I have in here holds 80 gallons, or in this case, 80 joules. Let's just say that that's how much it stores. It could be a big tank like Pete suggested. It could be a little tank like we started off with, but it doesn't really matter what the size is. I'm just going to pick a size, and the size is 80 because it's going to work out pretty good with the numbers, okay? And we know that when we turn the valve on, how many watts go in? Does anyone remember?
120.
120, right. 120 watts goes in when the valve is on, okay? So what happens to the water level in my tank?
It rises.
It rises. How fast does it rise?
80 gallons a minute.
80 gallons a minute. Well, so let's say a second. Let's say a second. Okay, 80 gallons a second. And how big is my tank?
80 gallons.
Right. How long does it take to fill up at this condition? 1 second. Right. So what am I going to write here? I'm going to write 2 charts. This is time. Right? This is time. Okay? And I could write how much level is in the tank. Why don't we do that? Why don't we write how much level is in the tank? It starts off, this is tank, right? Starts, and it has 80 gallons, right? Starts off with 0 gallons. And as it's flowing at a rate that after 1 second, it fills up. So that's what happens to the tank, right? The tank went from the bottom, and as it was flowing, it's flowing at a rate. After a few seconds, it's up here. A few more seconds, it's up here, right? The float's coming up with it. But when it reaches 1 second, the float's at the top, right? What happens when it hits the top?
Valve.
The valve shuts off, right? But before we get there, let me just draw something. I don't want to get ahead of ourselves because I want to talk about power. Yeah, I want to talk about power. I want to draw 2 graphs here. This is power. All right, I'm going to draw 2 graphs in 2 different colors. Power in, all right, power out. Okay? During this time where the valve is open, what is my power in?
120.
That's right. It's 120. So up until this 1 second, it is at 120. What's my power out during this whole time?
40.
40. Good. We're all paying attention. It's pretty basic stuff, right? It's not hard. But I think I'm getting the sense that it's somewhat eye-opening, right? Even though it's very basic. 40. But now, at the 1 second point, right? What happened? Just tell me what happened. Forget about these graphs. Just what happened?
Power in drops to 0.
The power in dropped to 0. Why?
The valve shut off.
Because the valve shut off. Why?
Because the tank was full.
Because the tank was full. Right, tank filled up. That's what happened. The valve's at the top. It shut off the valve, and it had the result that the power dropped to, the power in dropped to 0. Okay? The valve shut off. Shut off. No more water's going in.
It's a sine wave.
It's not a sine wave. It's not a sine wave, but the power input dropped to 0. What happened to the power output? To full tank with this opening? What happened?
It's constant.
It's constant, still 40, right? So during this transition, this is still going, right? And what's happening now when you have no water coming in and you have 40 gallons per second going out? What's happening to the level of the tank?
Oh, drain.
It's draining. Wow, it's so simple, isn't it? You're probably wondering what the heck I'm talking about because this is so simple, right? We're going to get there, okay? It's important. Baby steps. How long is it going to take for this 80-gallon tank to drain? If it's draining 40 gallons per second,
2 seconds.
2 seconds, right? This is going to drain, right? This one's a little tricky if you're not used to this sort of thing. How many seconds after I started is this?
3.
3, right? Because it's going to take 2 seconds to drain, but we're starting at the 1 second point. So this is going to be at 3 seconds. But this is 2 seconds long. It's going to take, and it's going to go down, down, down to where? To 0, right? To 0. So during this window, let's look at what's going on with power in. What's the input power during these 2 seconds?
0.
0, because the valve's off, nothing's coming in. Input power is way down here at 0. What's happening to the output power during this time?
Constant.
Constant. It's always going out at 40 watts. Now here's the $1 million question. What happens from here on out?
I think the process repeats itself.
You got it. The process repeats itself. We call that, it's cyclical. It's a cycle. It's going to do the same exact thing. So do I need to walk us through it again? Not really. We can walk it through real fast. So now the tank is empty. What happens? The valve turns on. It goes to 120 watts. 120 watts in, 40 watts out, 80 watts per minute, it fills up. Takes 1 second to fill up the tank, right? It's repeating this part, right? So let's draw it. It's going to repeat that part, 4 seconds, and 2 seconds after that, which is 6 seconds, it's going to go down there, right? The power is going to come up. It's going to stay that way for 1 second. It's going to go down. It's going to stay that way for 2 more seconds while this power stays the same, right? It repeats, and it's going to repeat every 3 seconds, right? This is what it's doing.
So is that
Over and over and over again, forever.
is that
Okay?
the frequency?
That is the frequency. You can call that a frequency. You can say that because this repeats the process once every 3 seconds, it's 1/3 of a hertz, right? You could say that. 1 cycle per 3 seconds, right? But that's getting ahead of the game. We're focused on energy and power. That's a good observation. We're going to see that that's exactly what it is. So I built this system. All I did with the system is I added a little float valve in here, right? You know what's beautiful about this system? It's a system, which means, goodbye tank. For all I know, what's going on in here is some electronic circuit that instead of having transistors and diodes and bridge rectifiers like before, it has inductors and transformers and some other gizmos that I don't know how they work, right? But I'm telling you that it's behaving this way because it could behave this way. Because I could do it with a valve, and I could do it with water, and I could do it with a float, which means I can do it with electronics too. I can do it with engines, I can do it with any sorts of things, but this is the behavior. And now I'm going to ask you as managers, as people who work with electronic devices because you buy and sell them and you work with them, what's the efficiency of this system? Now, you may not feel confident that you can answer that right now. But let me ask you this question. Do you think that it's possible for you to answer that right now with what I've showed you today? Do you think it's possible to answer that?
Yeah.
Why is it possible? What do you know? What if I told you that you know that is all you need to know to answer that question?
Is we know what the power out is and we know what the power in is.
Can you come up here and take over? You got it. Now you can't answer anymore because there's some other silent people still here, right? So Eric, you get it. Pete, you get it. Okay, so we're narrowing it down to people who can't get it. Or maybe you get it, you're shy. We're going to find out. Okay? We're going to find out. So let's talk about the power now. This system had 120 watts coming in, it had 40 watts coming out, and it was 33% efficient. Let's find out how efficient this is. Okay? We did it this way. If you filled up the tank with water this way, okay, instead of just letting your hose run and go over the top of the pool, you're going to fill it up to a certain level and let the sun evaporate, and when it gets an inch or two down, you're going to fill up it again. That's what we do every day, right? We don't just let it pour over because that's not efficient, right? We're going to try something that's a little more efficient. All right, so let's try it. So the trick here, okay, is that power is not continuous on our input. It is continuous on our output, so we can say power out is 40 watts all the time because it's always 40 watts. But what can we say about the power input? It's a little confusing. Someone might say, well, it's on for 1/3 of the time and it's off for 2/3 of the time, so maybe it's 1/3? Yeah, maybe, but maybe not. Like, how can we say it certainly is? Let's go back to energy. Let's go back to the M&Ms. Let's look at it like this. Conservation of energy is going to come and help us with this problem again if we're not sure about what to do with the power. Because power is simply a flow of energy. It's how many units go in the system per unit time, how many leave the system per unit time. So let's talk about this. In the first second, how much energy units go into the system? How many M&Ms go into the system?
120.
Hmm?
120.
120. Can you say why it's 120 units?
Because the valve's open.
Yeah, the valve's open.
Right, the tank is empty.
Tank is empty.
Okay, the rate is 80 watts per second.
No, it's 120.
120 per second, but
And
it
it's
goes up
and it's for what duration?
1 second.
Right. So in this 1 second, okay, that's gone by at a rate of 120 M&Ms per second, After 1 second, I have 120 M&Ms went in, right? 120 went in during this time. So I'm going to write this. 120 went in, right? How many left the system during that period of time?
It's 40.
40, right? So during this period of time, I had 120 go in and 40 came out, right? During this period of time, from 1 second to 3 seconds, how many M&Ms go in the system?
0.
0, okay? Why is it 0?
The valve's off.
Valve's off. So 0 went in during this time. How many left during this time?
80.
80. Minus 80. Okay. Now, it's fair enough to say that after 3 seconds, this process is going to repeat, right? Which means in the next cycle, there'll be another 120 that come in and another 40 that go out and then 80 that go out. So let's ignore that for the time being. Let's just ask what happens in the first 3 seconds of this system, okay? How efficient has this system been at moving M&Ms, okay, in the first 3 seconds? Well, how many did I put in the Ziploc bag to send to my friend down the road in the 3 seconds? 120 plus 0 equals 120. So in the first 3 seconds, I put 120 M&Ms in a bag and shipped it out, right? And how many got to my friend right here? How many got to my friend right here?
120.
40 plus 80 is 120. How efficient is that?
100%.
100%. Why? Not a single M&M fell down a sewer grate or went down my courier's mouth, right? They all got to my friend.
He was a diabetic.
It might have been a diabetic. That's terrible. But apologize to all the diabetics. 100%. So did we do better? Well, yeah, we did do better. We did a lot better. Guess what this is?
Switch mode power.
This is a switch mode power supply. This is a power supply that only turns on or turns off. That's why it's called a switch mode power supply. And it has a storage unit inside of it. It's called a tank. In some cases, it's an inductor and a capacitor storing energy. And it has a load, which is connected to an LED in our case, right, in our applications, but could be connected to anything. And it tries to be 100% efficient, okay? In practice, it can't be 100% efficient. And I'm going to tell you why. Well, in the analogy, is there any valve in this world that I could turn on instantly? No. They have some with a thing that takes you a couple seconds to close it. They have some that may be quarter turn, but still takes you some time to open and close it, right? You could try to maybe just slam something in front of it, but if you watch it with a stop motion camera, it's still going to take some time to shut it off, right? It takes some time to turn it on and off, which means this is not really going to shut off when you tell it to. It's going to take a little time. So you're going to get a little spillage, a little bit's going to fall over the top. If you put it, now you might say, well, I could put the gauge a little before the top so that, you know, it makes up for that. And there's lots of tricks like that. But also, the piping has some resistance, right? So it takes some energy away from what's coming in when you put it in. There's a lot of practical reasons, okay, why you can't get it to 100%. But even if you get 90%, it's still a lot better, 33%, okay? So now we've talked about conservation of energy, we've talked about power, okay? And we've talked about efficiency, and we've introduced how these terms can help you understand where your power is going in your product. Most of the times, things we struggle with is heat. Where's it coming from? Where's it going to? How to manage it? That's a whole art into itself, thermal management. But to answer a question like, how much am I dissipating? It's always that, okay? So now I'm going to talk a little bit about power. We're going to get rid of this. I mean, now we know how a switch mode power supply, what's the fundamental principle behind switch mode power supply, and what's the driving force? It's because we can aim to get 100% efficiency, and it's because we're never, doing anything other than turning fully on or fully off, and we're using storage elements inside the unit to help store it. but I want to talk to you a little bit about how to apply this in your everyday, day-to-day when these questions come up. Again, remember, I told you when I started today we weren't going to really talk about, a driver or a data sheet or any of that stuff. We're going to do that in the next session, because I think that's what will bring some more specific purpose to this. But I could tell today that, from some of your inability to, immediately upon inspection answer some stuff, that we learned some things today, and that's important because these are fundamental. These are the feet you stand on. If you don't know where they are and that they have a footing, you can still do some things with your arms, but it's a lot more helpful if you have a good understanding of the fundamentals. So we talked about this, which was if I know my power going in and I know my power going out, okay, I can tell you what my losses are here, because this equals power in minus power out due to conservation of energy. And I know what my efficiency is, okay, because I can say it's my power out divided by my power in, right? What's kind of interesting about this is that if I don't even know how much my power in is, okay, but I do know my power loss and my power out, I can also derive this, right? Because let's just look at this really quickly. Power loss equals power in minus power out. Let's say I don't know what power out is. Well, I can say this, minus power loss, these cancel, plus power out, right? These cancel, I get power out equals power in minus power loss, right? Can now substitute that in here. Power in minus power loss. That's also efficiency. See, I can play with these numbers. So I don't know how to measure the power input. It's 277 volts AC at 50 hertz and some weird application, and the current is some wacky waveform, and I don't know what it is. But what I do know is I do know that I have 3 watts of heat coming out of here, because somehow I can measure that, and I know I have 40 watts coming out from over here, okay? I can still get my efficiency, right? Well, let's use the other example. I had 40 watts coming out, and I had 80 watts of heat coming out. But I have no idea how much power is going in. How efficient is this system? Well, it equals, I must have messed something up here because I should have replaced power. I was saying I didn't know power. Let's redo this, right? Let's back this up. Energy, or the efficiency, equals power out over power in, right? So what I want to do here is I want to substitute power in, because I don't know what that is, right? So what I do is I say power loss equals power in minus power out, right? I want to find something that tells me what power in is so I get rid of it. I say plus power out, right? These cancel. I get power in equals power loss plus power out. Power in equals power loss plus power out. Now we have it correct, okay? Now we have it correct. I was doing it the opposite way around that I was practicing earlier, but I want to do it this way now. So this is correct. So now let's put in the values. Power out is 40. Power loss is 80. Power out is 40, right? That equals 40 over 120. Look familiar? That's the 33% we had before, right? Apologize for that mistake before. Just wasn't thinking straight. But now we have it right, okay? So I did not know what my power input was, but I could infer it due to conservation of energy. I know that whatever I put in equals everything that's going out. So if I add these two together, without doing the math just helps us verify it because we know we didn't make any mathematical mistake. But look at it from a conceptual standpoint. If what goes out has to be what comes in, okay, then these two have to add up to that, right? So if I didn't know what this is, this simply equals these two together. So it's 120. So I was able to figure out my efficiency without even knowing how much power is going in if I know how much is lost and how much is going out. The bottom line is if you only know 2 of these 3, you can answer the question, how efficient is the driver? Okay? So now I'm just going to quickly talk about, because we're really running out of time, we're almost there. We probably have about 10 minutes left according to my watch. And I don't think that's enough time to do a lot of stuff, but I do want to talk a little bit about how to compute power in the electronics that we work with, okay? So I'm going to quickly talk about two things. One is AC power, and the other one is LED power, since these are two things that we work with a lot, okay? I know we've spent a lot of time, so I just ask you to just try to stay focused with me, because now we're going to get into something a little bit more dense. I told you that power equals what? Who remembers? Pete can't answer. Eric can't answer. Okay. Who was paying attention? What's power in terms of?
Joules per second.
Joules per second. Okay, that's good. But in electronics, I have a device, any device. Could be a resistor, could be an LED, could be anything. I only care about two things usually in electronics. There's only two physical properties that I care about. I don't care about its diameter. No offense to the MEs out there. I don't care about its length. I don't care about its chemical composition. To any chemical engineers out there, really don't care. I only care about two electrical properties, and that is the voltage that's across it and the current that's flowing through it. Because those are the only two things that electronics really in the end cares about. You might argue, no, there's electric fields, there's magnetic fields. Yes, yes, yes. We're not going to go there. We're going to just say that this is all we care about for now. What's power in this term? Do you remember what I said earlier?
Volts.
Volts
Amps.
times
Amps.
current. It's voltage times current. I told you I was going to give that to you. I wasn't going to prove it to you, just to take it as face value. That's exactly what it is. So if I know the voltage across my LED and I know the current flowing through my LED, I know the power. Good news is that most times in LEDs, the signal that you see across here is flat. There's no change in time, right? The volts will be like that. That's not always the case. You might see some ripple from a power supply on here like this, but that's close enough to an average, right? You might see PWM, and that would be a problem.